Okay, so this is going to be the first of 2 lessons for now on related rates. These are word problems applications. We call them related rates because they are questions about rates of change, and as one length is changing, or one variable, one value is changing, how does another one change as they are related? They're going to be dimensions of shapes, or distances, or all kinds of things, and so they are relationships between rates, so we call them related rates. Okay, and we're going to do 3 different types of these questions, and there's a little bit of overlap between them in some cases, but generally speaking, we'll sort of have 3 different types, and we're going to do 2 today and then add 1 more new type tomorrow. As always with applications, with word problems, until you have done enough of them and gained the experience that's required to know how to solve them, to know how to work through them, many students struggle with how to get started, just what to do first. They're looking at the picture, at the problem in a big picture sort of way, which is overwhelming, so you have to break it down. So here are some, what I'm calling advice, but really these are sort of steps to get you started. And generally speaking, when you tackle any new problem, you're just going to start doing these things. Whatever comes to you first is fine. The order doesn't really matter. I usually draw diagrams first. Diagram's not even in here. Draw a diagram. Oops. But again, order doesn't necessarily matter, and you don't always need to have a diagram. I do like to draw them, but often they end up not having a lot of purpose. They don't have a ton of descriptions on them necessarily, so you don't have to, but it is another good sort of strategy, a good thing to get you started, so you can visualize the problem, which can be very important. Okay, so one of the things that you're going to do is, what is everything being compared to? It's almost always time. In fact, for us, I think it might always be time. There are a few questions that we have done, but I think in these circumstances, I think they have all been cut out. So once in a while, things are being compared to lengths as opposed to time, but it almost always is time, and you will be able to tell what everything's being compared to by the rate that you're given. You're always going to be given some rate, and you can look at that rate to see what things are being compared to, and that's going to be important. I'll talk more about that when we get into the first example. Okay, this is a big one. Identify and define variables. So the nice thing about a diagram is that it allows you to define a variable. If you've written an equation, some of this stuff is going to be measurement. Like the first one is talking about a sphere. So R, it's a given that for a sphere, R is the radius. But if you draw a diagram and label R, then that is defining your variable. If you don't draw a diagram, then you would have to do let statements to define your variables. Okay, and this also is useful when you're doing this, when you're labeling your diagram or whatever it is, to think about which ones are changing and which ones are not. Again, when we get into the first few examples, this will become clear why this is so important, but this is something to think about. So if something's not changing, I'm going to make a note of that. It's really important. If something is changing, then something else important happens to it. Okay, we're going to write down formulas that we're going to use. If we're talking about volume of something, you write down the formula for volume. This is actually a strategy if you're stuck, because if you write down the formula, then you can see what variables are in there, and that might help you start to think about what values you need in order to solve the problem. So just writing the formula, even if you're not going to use it yet, writing it down and allowing yourself to sort of think about what variables, what values are required for the formula, can actually help you get moving on a question. So write down any formulas that you might be using. Sometimes that's going to happen after you've drawn the diagram, because then you're going to realize what kind of a question it is. State any givens. We're always going to do this. Sometimes you're given many things, sometimes you're only given a couple, but write them out. It's a really good thing. State what you are solving for. Again, this helps you have focus, and when you are writing out formulas and you realize, okay, this is the thing that I'm looking for, so I need to have all these other values, it does give you a direction. If you are stuck and if you are feeling confused about what to do, you have to go back to these structured steps and just force yourself to do them and use these strategies. If I have a formula that has 4 unknowns and I'm solving for one of them, I need to have the other 3. So if I wasn't just given them in the question, then I have to be able to find them. And then there's your focus. Now you know what you have to do. Well, I don't have this X value, so how am I going to find it? Okay. So stating what you're solving for is really useful. Stating givens. Differentiate. Duh. Okay, this is calculus. We're always going to do that. I often make this joke in these kinds of questions and others, where if you haven't taken the derivative at some point, you've done the question wrong. And this does come up. This does happen. Probably less so in related rates questions, more so in other types. But people do, on tests, put down a solution to a problem, and at no point they've taken the derivative. And so you can pretty much guarantee that that's wrong in the calculus portion of this course. Okay. The last one, this is the strategy we're going to add to things tomorrow. Substitute. Okay. Sometimes substituting will make it easier. It's not always necessary to do. Sometimes there's more than one method to solve questions depending on exactly how it's asked. But substituting can often make questions easier, and sometimes it is necessary. But we'll talk about that in the next lesson. Now, here's a really important note. If something, so one of your variables all represent things that could take on different values. If it's changing, you cannot sub in for that variable until after you have taken the derivative. That being said, if something is not changing, okay, so this is when we say which ones are changing. If something's not changing, subbing in first will actually make things easier. So that's a good thing to do. So that's why we're going to identify which ones are changing and which ones are not. But be careful. If you're not mindful about this, people do by accident, I suppose, sub in for something that's changing, and then the question's not going to work out. Okay. So whenever you're stuck, come back to these few pieces of advice and just think about them in a very straightforward, structured way. Okay, I don't know what to do. I'll try this. I'll do this. I'll state my givens. I'll start writing formulas, that kind of a thing. Okay, and again, as we go through different examples, I'm going to go over other tips and other things that you can think about that should help you move forward if you get stuck. You'll notice I've already done the diagrams just because they're a little bit trickier to do and they take a bit of time on the computer to make them look nice. So I've got them drawn in already in most cases. If you need to pause the video to draw it out or to write down the question, go ahead and do that. But I'm going to get started. So first question, a bunch of the questions today are just going to be about measurement. So that's sort of one type. And like I said, sometimes there's overlap, but we'll talk about that in the next lesson. So, it's about a sphere, it's about a cone, it's about some kind of probably 3-dimensional, sometimes 2-dimensional, sometimes just a rectangle. And that's sort of one type. And these are pretty straightforward. You're just going to use the equation for volume or surface area or whatever it is. But occasionally they do have some extra steps involved. And so, we'll deal with those as we come across them. So first question, volume of a sphere is increasing at 100 centimeters each second. So that's actually usually written as 100 centimeters cubed per second. So that is a rate. And what is this rate in terms of? It's in terms of seconds. So this question is in terms of time. And so this is where I say, when you find the given rate in the question, that's going to tell you what everything is being compared to. And it's almost always time. So it's going to be seconds or minutes, generally speaking for us. And so there you have it. That's how you know. If it was centimeters cubed per centimeter, okay, then time isn't relevant and it's being compared to centimeters. As the radius changes, how does the volume change? But I don't believe there are any of those questions now. We've sort of cut them out because we've condensed things and we're not doing all the different kinds of questions that we've done in previous years. So find the rate at which the radius changes when it is 25 centimeters. The fact that we are comparing this to time, but we're doing all these different measurements, that's going to make every single one of these questions implicit. These are all implicit, and that is one of the sort of maybe strange things when you first start doing this, that often when we have an x in our question, we're taking the derivative with respect to x. But in this case in particular, in almost every case, we are comparing things to time, so we're taking the derivative with respect to time, and so that means that every one of these questions is going to be implicit. And so we're going to use that particular notation to define these variables, and it's going to be very helpful. Okay, so I'm going to add one more little thing here to my diagram. There's r, that's the radius, so I've defined that variable. Okay, and the only other variable we're really going to need is v for volume, but when I write out the formula, that's good enough. You don't have to say let v represent volume or anything like that. Okay, so there's not a lot. There's not a lot going on in this one. It's pretty straightforward. So let's start stating our givens. So find rate of the radius, the change in the radius when the radius is 25 centimeters. So there's a given. Radius is 25 centimeters. And the only other value it gives us is the rate at which the volume is increasing. So we're going to call that dv by dt. And that's 100 centimeters cubed, again, per second. And we are going to be finding the rate at which the radius is changing, dr by dt. So notice that I'm taking the derivative with respect to time, because that's the rate that things are being done in, right? And so again, that's what makes it implicit. And this is it. This is basically enough for us to get started. We were given these two values, and we're told to find that rate. And again, notation is going to be important, so I hope you understand that that's how we express that this is a rate and that that's just a length. If you're doing all of the homework and you're thinking about this stuff, you probably will be able to memorize these formulas, but you don't have to. We will give you formulas if they are strange ones, or if it's something that you don't know, you can ask. There will be cases where you should know them. We're not going to give you formula for area of a rectangle or area of a circle. Like, these are ones that you really should know, but I do know that some people probably don't have the volume formulas memorized. You should try, but there will be circumstances where we might be able to give you those formulas. Okay, I would say try to memorize them. If you do the work, if you do all of the work, then you'll probably get to know them, be reminded of them because you've memorized them in the past, and without even really trying. Okay, so I'm going to take the derivative. So when I multiply through by this, I'm going to multiply through by the variable. Pi is not a variable. Pi is a value, so that is it's a constant, right? So my only variable on the right side is r. So I multiply by 3, and that is going to cancel out this 3 in the denominator. So I'm left with 4 pi r, reduce the exponent by 1, and then don't forget, because it's with respect to time, I need to have the dr by dt. And if you imagine you didn't do that, well, that's what we're finding. So that's going to be a problem. Again, stating out what you're finding is not a requirement for full marks necessarily for me. That's to help you. That gives you focus. And if you take the derivative and you don't have the thing that you're finding, then you've done something wrong. So that will help keep you on the right track, kind of thing. If you just want to see that extra step, it was dv by dt equals 4 over 3 times 3 times pi times r squared dr by dt. So this does take some getting used to, but it's the same thing every time. And then those 3's divide to 1, and we're left with the step that we have here. Okay, now I'm going to sub in. dv by dt is 100. R is 25. Okay, and now we're just going to move things over and isolate for dr by dt. And you don't need to show a lot of steps here. You can do this sort of as fast as you want. I usually do it kind of in 2 steps. So I'm flipping sides here, but I get 100 over, and I'm dividing by all of that, right? So 25 squared is 625 times 4 is 2500. So I've got 2500 pi, which reduces to 1 over 25 pi. And in some circumstances, you might be asked to round. In other circumstances, you might be asked to leave your answer exact. So when it's not stated, I always do both because I think it's good practice. So on my calculator, I do 1 over 25 pi, and I get 1.013. The 2 rounds up to a 3, and that is that. But if you're asked for an exact value, then it would have to be fully reduced, and in this case, it's going to be in terms of pi. So this is one sort of thing that you want to be aware of and getting used to, is that these questions that involve some kind of a circle, spheres, cones, or just circles, we're going to have a pi in the formula, and we do need to know how to take the derivative in terms of pi, keeping the pi in there, and how to sort of simplify your answer to be exact in terms of pi, 1 over 25 pi, okay? So now the very last part of these is on a test, you're going to need to do a proper therefore statement. Obviously, in your homework, you're going to do whatever you want. But we don't just say the rate of change is this. We say, therefore, the radius is... So because this is a positive rate, the radius is increasing. And if you remember in MHF, we made a big deal out of this as well. We had questions at the very end of the course where we interpreted a positive or a negative final value as an increase or a decrease. So this is increasing by 1 over 25 pi, and that is centimeters per second, I believe. Because we were working in centimeters, it was centimeters cubed per second, so this is centimeters per second. If you're asked around, then you would put the rounded answer. If you're not asked either, then you could put either, but it would be a good idea in your solution to show both, show the reduced exact value, and then if you want to round it, that's fine. If the question says exact value, then make sure you follow that. Notice that this question says, find the rate at which the radius changes. Some questions will say, find the rate at which the radius is increasing. It'll tell you it's increasing. So for me, technically, then you don't need to really do this part. I don't even know if you need a therefore statement at all. If you did, you could just say, I don't know, it's still natural to say the radius is increasing by, but if you even skipped the therefore statement at that point and you just put units on your final answer, that seems to me that would be appropriate. The fact that this question says, find the rate at which it is changing, so it has not said whether it's increasing or decreasing, you absolutely have to add that in your therefore statement. Don't just say the rate of change is 0.013. Or don't say therefore 0.13 centimeters per second, right? You have to state what that actually means. That's part of the question for full marks. Okay, let's try another one. So this one is another measurement, but just 2 dimensionals. Looks like a rectangle. Length of a rectangle is decreasing by 1 centimeter each second, while the width is increasing by 2 centimeters each second. So there's something in there that might have been subtle, but it's actually really important. So we'll talk about that when we start listing our givens. But this is a big deal, something to really make note of, and we'll see it a few more times over this lesson and the next one. The width is increasing by 2 centimeters each second. Find the rate at which the area is changing when the rectangle is a square that has sides of 10 centimeters. So you do have to be able to read through these and understand all the things that you're being told, all the important information. And every question is going to be a little bit different, but it will always come down to those sort of strategies that were laid out before, okay, at the beginning. So I'm going to, again, define my variables by just labeling them on the diagram like that. And we are told to find, dA by dt. Okay. So when we are finding dA by dt, the length will be 10 centimeters and the width will be 10 centimeters. So it's giving us both. That doesn't always happen. It did in this case. And that means it's a square. So that's what it's telling us. When a rectangle is a square that has both sides, the length and the width of 10. And some people are going to go and find the area. Oh, the area is 100. That's useless to us. Now, if you do that and it ends up being useless, that's fine. But it turns out we don't need to know that. It's not helpful. And again, that just comes with experience. But like I said, if you find that, you're not going to lose marks because you did something you didn't have to do. You'll waste some time, but not much. That doesn't take very long to find that. Okay. So what else do we have? We have the rate of change of the length and the width. So we have dL by dt and dW by dt. But what is different about these? I want you to think about this. So the rate of change of the length is 1. Again, look at centimeter each second, so centimeter per second. So we know that we're doing things with respect to time here. And the width is increasing by 2 centimeters per second. I do like to include units when I'm listing these, just because when I go to do the answer, I've got them written out here and I don't have to look back at the actual question. And just to make sure, you'll see that sometimes we're given centimeters and meters. So it can be, it's just a good habit to write out units to make sure that everything's in the same unit. So hopefully you picked up on the fact that the length is decreasing and the width is increasing. So what do we do with that? Do we just ignore it? Turns out this is a really big deal. This is really important. And if it's decreasing by 1 centimeter per second, then that rate is going to be negative. And if it's increasing, then that rate is going to be positive. So this is a very important point, that when it says something is decreasing, and it's not always going to say it's decreasing. Sometimes it's going to give you this in a different way, and the diagram maybe is what's going to tell you this, but you absolutely have to have that negative in there. To make everything work, right? To make this all make sense in the final question. So I think we have our givens written out. We've written down, we've defined our variables by drawing and labeling the diagram. We've written what we're going to find. This is talking about area of a rectangle. So I'm going to write out the formula for that. Area equals length times width. And so now we're going to take the derivative. Now, what do you notice when we take the derivative of this? L is changing and W is changing. They're both changing. They both have rates. So that means this is product rule. Okay, this is really important. People miss this, and again, this is a big deal. If you make a mistake taking the derivative of this because you don't recognize its product rule, you're going to lose a chunk of marks. That's a big mistake. So dA by dt. So the derivative of the first times the second plus derivative of the second times the first. So it's a little bit more complicated than we might have recognized in the beginning. But because we have all these values, this is what we're trying to find. Look, we have 5 unknowns. The one we're trying to find, 2, 3, 4, 5. We've got 5 unknowns, but we've got all 4 of those. There they are up there. So we've got 4 of them. We can just sub in and solve for the 5th. And notice there is no A. So we don't need the actual area. It doesn't matter that the area is 100 in this case. So the change in length is -1. And the length and the width was 10, and the change in width was 2, I believe. Yep, there it is. And again, the length is 10. And so this ends up being 20 minus 10, which is 10. And so it's positive. Could it be that the area was decreasing? It's possible. If the rates were different, then it's certainly possible. And so we don't just take it for granted that it's definitely increasing. It could be decreasing. So this is something that we have to interpret. Therefore, the area is decreasing by 10 centimeters squared per second. Okay. We're going to do a bunch of examples for this first lesson. So this one's very different. This is the second type. We did 2 that were measurement. There's another measurement question. This is a different type. It doesn't talk about area at all. It's all has to do with lengths. And so this is going to be a Pythagorean Theorem type of question. Okay. A plane is flying north at 600 kilometers per hour. So that's obviously this one, and I like to put a little arrow on it. And I usually put it sort of in the middle, because if you put it on the end, it, I don't know, usually just doesn't look nice and it kind of gets lost. So I put them in the middle to show the direction. Passes over GCI at noon. Another plane flies east over GCI. So this one's going this direction. Now, if you mess up your east and your west, nobody messes up north and south, right? That's easy, up and down. But people do get east and west backwards. I don't care if your diagram looks wrong, as long as you get the right answer. So you just have to be careful about which direction you're going, I suppose, to make sure that you have your arrow pointing in the correct way. I hope that makes sense. Okay, so it flies over GCI at 540 kilometers per hour. Again, notice that our rates are given per hour. So again, this is with respect to time, and it passes over GCI at 1201. If the two planes are at the same altitude, turns out it's a lot harder if they're at different altitudes. Usually the questions that we go over, we just take for granted that they'd be at the same altitude. How fast are they moving apart at 1206? So we need some values that we don't have, and it's just going to be a little bit of extra work to get them. They're not given directly, but they're going to be easy to find. But this does sort of point out this type of question, and sometimes what can happen when we're given these rates and we're given time. We're not given any length. We don't actually know how long this is the problem. So I am going to define my side lengths, define my lengths as x, y, and l for length. Which variables you choose doesn't matter. You might be tempted to use d for distance. I often am, but then when we take the derivative, we get dd by dt, which is a little confusing. It's fine. It's not wrong if you do it that way. It's just, I think, something that tends to be avoided. So I often use L or sometimes H for hypotenuse for these kinds of questions. Or sometimes people use R for radius from trigonometry, because we're used to doing that in there. So you'll see that a lot. Those are the common ones, but you could use ABC if you want, for that matter, right? Because we use those in Pythagorean Theorem very often. Now, I'm going to point out a different order that you might do this question in. If you recognize that this is a Pythagorean Theorem question, what is it that relates these lengths with this length, right? What's the formula? It's Pythagorean Theorem. Okay, so it is L squared equals x squared plus y squared. All of these things are changing. Okay, x is changing. That's one plane flying. Y is changing. That's the other plane flying. And L is changing. If you think about it, L is getting bigger as x and y get bigger. L is also getting bigger in this case. It could be getting smaller, but the point is, if you visualize what's happening here, L is increasing. So we can't sub anything in. So if I were to take the derivative, now this is not normally the way that I would do this question. I would start to list givens. But what I want to point out is an example of what you might do if you're stuck and you're not sure how to proceed. I know that this is a Pythagorean theorem question, so I am going to take the derivative of 2L dl by dt, right? So the 2 comes down, and we decrease it by 1, so we still have L to the 1, and then dl by dt, because this is implicit, because it's with respect to t, 2x dx by dt, plus 2y dy by dt. And I also am doing it this way because we can notice that in every one of these questions that is Pythagorean theorem, these 2's will divide out. Okay, so normally I write them to be to be careful to show how the derivative is actually being done, because it is coming down, but then I divide through by 2 and I don't show that step. They just kind of disappear in the next line. Okay, so it's obviously fine for you to do that as well. Usually I would actually sub in at this step, so you wouldn't have to write it twice. So it's not any extra work, but there's a reason why I'm not in this case. Now I'm looking at this and I'm realizing that I have an equation. What are we supposed to be finding? Let's do that first. How fast are they moving apart? So notice how it tells us that it's increasing, right? It tells us that it's moving apart. So that is, sometimes that happens. How fast is it moving apart? So we are supposed to be finding dl by dt. So first of all, does my equation have dl by dt in it? Yes, it does. I'm finding the rate of change of the distance between the two planes. One plane's there and one plane's there. Distance between them is L. My equation has that. Good. It has 5 other variables, 5 other values. So we need all of them, right? This is the whole point, is we need to have all of these variables. So now, if you are stuck, this is a strategy. If you, as long as you know the formula that's relating the values, you could put that formula in and take the derivative and look at what variables are left in the derivative, and then use that to go back and try to find all of them. So a few of them are given. A plane is flying north. That's our x. So the rate of x dx by dt is positive 600. Okay. Might need to move this out of the way. Whoops. And we have the rate of y. It's 540. And it's increasing, both positive. We don't have x and we don't have y. How are we going to find those? So that's the little bit of extra step that we have in this question. So you can stop, you can pause the video and think about this for a second. I'm sure many of you will be able to figure this out. Okay, but this is how we're going to do it. To find x, that's the plane flying north. It's going at 600 kilometers per hour. It flies over GCI at noon. And now we're asking a question 6 minutes later at 12:06. So it's been flying 600 kilometers an hour for 6 minutes. But this rate is in terms of hours. So I am going to convert the 6 minutes into hours. And in order to find x, so again, this hasn't even that step, which, when somebody shows you how to do this, it makes sense. But coming up with this kind of stuff on your own in the middle of a test can be difficult, because it's not something we do all the time. So 6 minutes out of 60 turns this into hours. Okay. And that gives me 60 kilometers. We'll do the same thing for y, but y has only been going, because they are at the same altitude, they couldn't fly over GCI at the same time. So the second plane has only been going for 5 minutes, because it crosses over our school at 12:01. So 540 times 5/60. And turns out that gives us 45. We're still missing one more, aren't we? We're missing L. How are we going to find L? With Pythagorean theorem. Now you might say, well, how am I supposed to know how to do that? Well, when we take the derivative and we see that there's an L in there, we have to find it, and you just have to think about, well, how could you find it? And now that we've done one of these, and if you do the practice, you'll do more of these, and hopefully you'll get used to it, and you start to recognize that in many cases this is something that we have to do, that we're not given every value that we need, and some of them we have to go and find. So this works out to the square root of 5625, which happens to have an exact value of 75. So that one works out nice and perfect. If it didn't, you would keep the radical form. Do not round that answer, okay? Don't ever round until the very end. And now we have an equation with 6 variables. We know 5 of them, and we're looking for the other one. So this is perfect. We've got it. And we can just sub in. X is 60. Dx by dt is 600. Y is 45. dy by dt is 540. So I'm obviously going to simplify through there and then divide by 75, which is 60,300 divided by 75, which again happens to have an exact value of 804. Therefore, the distance between the planes is, increasing. So that's really important that you state that every single time. You have to state if it's increasing or decreasing. There are other ways. Sometimes we say falling, sometimes we say rising, something like that. There are other ways of saying it, but you have to say, basically make a comment on direction, increasing by 804 kilometers per hour. So just quickly going back over this, I did do this question in a little bit of a different order to point out that that's something that you might try if you're stuck. Generally speaking, I would list givens first, but these ones weren't given directly. So, if you listed the givens that you have, and then you go back or you do the derivative and realize you're missing some, then you would just go back and do it then. So again, order doesn't exactly matter. Try to keep your solutions organized. Leave some space maybe in case you have to go back. We had to do a little bit of work to find them. We had to turn a number of minutes into a number of hours. We had to recognize that we were given time in minutes that had passed, but our speeds were in terms of hours. You could have converted this to kilometers per minute instead and put everything in terms of minutes. Generally speaking, we choose not to change rates. It's a little bit trickier, but it wouldn't matter in the end. And if your answer ended up being kilometers per minute, then that would be fine. And then finally, we had to find an extra value, a final extra value that we were not given. Okay. And this was different from the first two in that it was a Pythagorean Theorem type of question. So lots of new little details in that one. Okay, we still have a couple more. 10-meter ladder is leaning against a wall. If the ladder is slipping out from the wall at the bottom at a rate of half a meter per second, how fast is the top sliding down the wall when, and we've got 2 different circumstances, so we'll get to those in a minute, okay? And they're giving us 2. It's not just doing the same thing twice. They are a little bit different. So a 10 meter. So now I'm going to start labeling my diagram. And again, the order that you do this doesn't necessarily matter, but take a look at this, a 10-meter ladder. So this is going to be my ladder, and I'm going to call it L for ladder or for length, okay? Leaning against the wall. I want you to think about what's important about this ladder. So what's important to think about this ladder is its length is not changing. It stays at 10 meters the entire time. So I always make a note of that. And again, you want to get in this habit of looking for things that aren't changing. This is going to make it easier when we go to take the derivative. Okay, so if the ladder is slipping out from the wall, so the bottom of the ladder is going this direction, and I'll call that X. And the top of the ladder is sliding down. And again, you have to be able to visualize this, but hopefully you can. If the ladder is slipping, then the bottom's going out that way and the top is coming down that way. Okay, and I'm going to call this h for height. Maybe you could just use y, that's fine. If h is confusing because it's also hypotenuse, go for it. You pick, like I said before, pick your own variables. Okay, and so that's our diagram pretty well drawn out. I'm going to start listing some givens. Sometimes what I like to do is list the givens that are going to be relevant to each part of the question at the very top. And then for A, we're going to be doing one thing, and for B, we're going to be doing something a little bit different. But again, how you organize your solution is up to you. And what else do we know? I'll give you a second to think about this. So we know dx by dt. It's positive 0.5 meters per second. We know one more thing. We know dl by dt. It's 0. You don't have to state this necessarily, but I'm going to show two slightly different ways of doing this question, and for one of them you would need to have that value of 0. In both cases, since we're finding the same thing, I'm going to list that. We are always finding dh by dt. Okay, and so those values are going to be the same for each question. For A, it tells me the bottom of the ladder is 6 meters from the wall, so that's telling me x is 6. When I take the derivative, I'm also going to need to know the value of h. I'm finding dh by dt. I've got L and dl by dt. I've got x and dx by dt. So I'm only missing one thing, which is h. So how am I going to find h? Again, Pythagorean Theorem. And again, this works out nicely to exactly 8. Okay, now I got two ways of doing this. So I can take the derivative. 2x dx by dt plus 2y dy by dt equals 2l dl by dt. And just start subbing stuff in. Again, the 2's are going to disappear. So x is 6. dx by dt is 0.5. Y is 8. Sorry, not y. H. Whoops. See, in my head I changed it. You probably noticed that, didn't you? H is 8. And dh by dt is what we are looking for. So that's still unknown. L is 10. Notice again that all the 2's disappeared. But dl by dt is 0, so that's just going to be gone. Okay? So the other way we could have done this, and honestly, this is the way I would usually do it, so this is what I would recommend, is if something is not changing, sub in for it. In this case, it doesn't make much of a difference, but in some cases it will make your life easier. So again, 2x dx by dt. Why do I keep using y? Plus 2h dh by dt. Derivative of a constant is 0, so it's just 0. So I'm getting 0 here, or I'm getting 0 here after I've subbed in. But this is a little bit less writing, a little bit less difficult to take the derivative, and in some cases it might even make it that much easier to find the derivative. Okay. So now I am going to isolate for dh by dt. And notice that 6 times 0.5 is 3. Move it to the other side, I end up with negative 3. Divide by 8, and I get negative 3 over 8, which is negative 0.375 as a decimal. I believe that's an exact decimal, right? 3 divided by 8. So we didn't round that, so leaving it as a fraction or as a decimal again in both cases would be totally fine. Therefore, the top of the ladder is, so I'm going to say this one differently, falling. So falling tells us that the distance or the length is decreasing, right? So falling at 0.375, we're talking meters per second here. Okay, that was just part A. Part B. Part B, the top of the ladder is touching the wall 4 meters up. So this one gives us h equals 4. So now it's giving us h and we have to solve for x. And this one does not work out perfectly, so it's root 84. Okay, 100 minus 16 is 84, so root 84. Calculators do this nicely for us these days, so you probably, if you can, want a reduced version of this. Sometimes that's a little bit easier when you're doing exact value stuff. Again, your calculator is probably going to do that for you. Again, we're finding dh by dt. Again, dl by dt is 0. But whichever one that you choose to do, whichever method, will again be fine for this one. I've already stated the equation and taken the derivative, so I'm just going to start with the derivative. I don't think for the same question you have to show that twice. So we've got x dx by dt plus y or h, keep saying y, dh by dt equals 0. Okay, so again, x is 2 root 21. dx by dt is 0.5. H was given it's 4. dh by dt is what we're solving for. Again, this is going to be negative. We know it's going to be negative. This is another good strategy. If you know by just visualizing that thing should be getting smaller, in some cases you will know, in some cases we won't. But if you know it should be getting smaller, then absolutely, when you're solving this, you should expect it to come out as negative. Notice that this 2 and this 0.5 cancel each other, so that's what I say. If you simplify things, sometimes it makes our life a little bit easier. I end up with negative root 21 over 4. When I move the root 21 over, it becomes negative divided by 4. And this works out to, not 0, negative 1.15. So again, therefore, the top of the ladder is falling. Just say it naturally, but make sure you include direction in your therefore statement at 1.15 meters per second. Notice that I don't include the negative there because I've said that it's falling. That's the whole point. I do not want to see a negative in there. I need that to be interpreted as a direction. One final example. Sides of a cube are increasing by 10 centimeters each second. So again, this one's in terms of time. So sides of a cube are increasing. So I'm going to call the side S. And that's telling me ds by dt is, they're increasing, so positive 10 centimeters per second. What is the formula for area of a cube? Are we talking area here? Oh, area. So surface area, not volume. I was thinking volume, but no, it's not volume. It's surface area, right? So you could call it surface area SA or just call it area. So that is, each side is going to be S squared, right? S. So S times S is S squared, and you have 6 of them. It's always a cube, so they're always going to be the same. So 6S squared. This is not an equation we would give you. This is something you should be able to develop yourself. You don't have to memorize the formula for surface areas because you can just develop them by thinking about the shape. Okay, if you need more review on that, go ahead and ask and we can talk about it further. But the way I just did by thinking about how this cube has 6 sides, each side is S squared, so I have 6 S squareds. That's not a formula that I've memorized. That's just making sense of it. Question A, find the rate of change of the area. So I'm finding dA by dt when the side length is 1 meter. If a side length is 1 meter, that's 100 centimeters. And I want everything to be in the same. And because my rates are in centimeters, it's easier to change 1 meter to 100 centimeters. So I chose to do that. So just watch for that. Be very careful that that's, again, like I said before, that's why I like to write out units and just be in that habit. Don't be lazy. Just do it, because then you can catch things like that. Okay. Take the derivative, dA by dt, 12s ds by dt. Do I have ds by dt? Yes. Do I have s? Yes. I'm looking for dA by dt. Done. (12,000 centimeters squared per second). B. So on a test, you're going to therefore, and you're going to answer it. Okay. And it does say changing. And because it says changing, you absolutely, in your therefore statement, you have to say that it's increasing. This one's obvious. Every side length is increasing. Of course, the area is going to be increasing. Of course, the volume, if it was about volume, would be increasing. I don't care that it's obvious. I still want you to say it. Okay, you need to say it. Find the rate at which the area is changing when the cube has a volume of 4,000 centimeters cubed. Okay, this is a good one. This is the reason why we were doing this. Oh, this one's volume. So it is a little bit different. But it is still asking about the area, rate of change of the area. So we're still finding dA by dt when the volume equals, what was it, 4,000? Yeah. Well, that's weird because volume's not even in there. So why is it saying volume? Well, take a look at this. When we take the derivative, what do we need to find the rate of change of the area? We need the side length, and we need the rate of change of the side length. Well, we have the rate of change of the side length, but we don't have the side length. So why do you think it's giving us volume? It's giving us volume in order to find the side length. So volume is side length cubed. We're given the volume as 4,000. That means side length is a cube root of 4,000, which is not a perfect answer or anything like that. So we'll just leave it like that. But there you go. So that's another example of how it gave us a roundabout way of giving us the information that we need. But because this was in 2 parts on tests, they're probably not going to be in 2 parts. It's going to be a single question. But you know, this is a nice for just learning about this. Because this was in 2 parts, we already had that derivative, and so I know that I need s. Okay, and so that hopefully tips me off that I can use the volume to find the sine length, because I knew I was going to need it. Don't start thinking, oh, maybe there's some other way of doing this. No. You just need to find the values that you need. Again, we already took the derivative, so I'm going to jump straight to that. So my side length is that cube root of 4,000. And our rate of change is still 10, increasing by 10. And so, you know, this is 120 cube root of 4,000, which is not really a nice way to do it. So I'm just going to round this one, and it turns out to be 1904.9 centimeters squared per second. Again, therefore, the area is increasing by that amount. Okay, so that was 5 examples. 2 Pythagorean Theorem examples, 3 that were just measurement. Well, actually there were extras in there because there were some parts A and B, but gives you a really bunch of different examples where you have some that you're given all the information you need directly, some where you have to find the information, some where you have to find multiple parts of information, sometimes little things, sometimes harder things. So, but it gives you a real sort of variety of the kinds of questions that you are going to get in doing these related rate questions. Again, we're going to do one more lesson on this in this unit, and in that lesson we'll do some more Pythagorean theorem questions. to go over those again, and then we're going to introduce the third type. But that is it for now.